So section 8.3 is where we bring pretty much the last 4 chapters together in terms of all sorts of equations we've learned how to solve. And a bit of an overall checklist of sorts of the different methods that we've learned. So it turns out that because of that very specific form we were looking for with the square root property, that will be the very first thing I suggest that you look at. If an equation is of that form, we want to utilize that now that we have that process and just jump right into it with that square root property. However, if we don't have that particular form, then we want to get it into the quadratic form. Now, to do so may require some work, as we've seen in the last couple chapters, whether in chapter 5, if it's not already in that kind of ax squared plus bx plus c form, it may require something like that kind of substitution to simplify it down to see the form. Or, if we're dealing with the rational or the radical equations, the steps of clearing the fractions or clearing the radicals. So that's going to be some review for us there. But once we get that form out of it, the quadratic form, then it's a question of does it factor? If not, does complete the square work nicely? And that's what A is kind of mentioning here, the idea of B being even or A being divided through. And lastly, our last resort, essentially, would be to consider the quadratic formula. So even though that formula we learned last section works on all of them, I don't want you defaulting to it. We got to make sure we understand these other processes and when they do work as well. Now, the very first question here is really just focusing on the idea of which form or which approach would we want to use for a given equation. This is by no means every single form, but to help us identify between the ones we've been working with here recently. So it says with which method is best used for each equation, and it does say use each one once, but I'll say it kind of lends itself that way as we do go through our checklist. So looking at this very first one, again, referencing the checklist above, this is definitely not in the form for a square root property. It is in quadratic form already, x squared x no x, but to look at it, if you attempted to factor, you'd be looking for an easy case number game with numbers that multiply to a -5 but add to a -5, and that doesn't work. So it doesn't factor. If we went on to complete the square, the issue is b right there, that -5, that's an odd number. So if we were to do the magic box, we would encounter fractions. So that leaves us with our last line of defense, which would be that this would be one we would use the quadratic formula on. All right, let's look at the next one over here. This form of something squared equals a number is exactly the form that we want to recognize as being the square root property approach that we would want to use. Taking the square root of both sides, getting the plus or minus in there. Basically, it's like the last half of the complete the square process, right? Just the last couple lines of it. Okay, this guy here compared to this guy here, these are our last two. Well, for this one, the 2 out front, if we were going to say, let's factor this, right? That's the question, does this factor? Well, let's go to this one real quick. The question is, does this factor? So as I mentioned, we're going to use each one once. X squared plus 5x plus 6. Can I find two numbers that multiply to +6 and add to +5? I can. So this tells us this will factor. Let's look over at this one and notice that if I were to say, I want to get rid of that 2 out front, I could divide everything by it, giving me x squared plus 4x minus 15 equals 0. So we notice that this guy, to find numbers that multiply to -15 but add to +4, that doesn't factor. So we're pretty much left with the complete the square process here. We've used the other 3. But I want to point out that not only did we get to divide the 2 out nicely, no fractions, but b is an even number, so your magic box will have no fractions. So this is a prime candidate for the complete the square process. So that's kind of the checklist, the mentality you want to use when looking at a problem and determining what approach you would want to use. So let's look at some problems here. This first one, this is going to be a throwback. This is a rational equation, so this would be like a chapter 6 problem. So remember, in chapter 6, to solve these, we want to clear those denominators, clear the fractions. We do so by first finding an LCD. To find the LCD, we want to make sure each denominator is factored, which it is. That's just x minus 5, and that's a 2. Now, each of those seems to be a unique factor, so it looks like our LCD is going to need to be each of those things. So that means we will take 2x times x minus 5 times each one of these fractions. All right, we always take it times every term, fraction or not, to keep the equation balanced. So we've got every single term multiplied by the 2x, x minus 5 LCD. Now here, the x's cancel. So you've got a 2, an x minus 5, and a 50. Well, the 2 and the 50 are easy enough to make 100 times x minus 5. Here, the x minus 5's cancel, so we're left with a minus or negative 2x and a 50. That'll give me minus 100x. And over here, the 2's cancel, so I've got an x times an x minus 5 and a negative. So the negative of x times x minus 5. So that would be what a line would look like once we've done some of that canceling and a tiny bit of the simplifying. There's still more to do though. Distributing gives me 100x minus 500 minus 100x. Distributing there gives me negative x squared and plus 5x. So it looks like we've got the 100x's canceling, knocking each other out when you combine them. Negative 500 left on that side, negative x squared plus 5x on that side. This is looking like something we can get into our x squared x no x form. Let's move everything to the left so that x squared is positive. So I've got that equal to 0 now. And then the question is, does this factor? Turns out it does. Two numbers that multiply to a negative 500, but also add to a negative 5 would be negative 25 and 20. So this does factor to x minus 25 and x plus 20, which means x minus 25 equals 0, giving me 25, and x plus 20 equals 0, giving me x equals negative 20. Now, the thing to remember, it's been a while since we were in chapter 6, we're solving a rational equation where x was in the denominator. So we do need to do a domain check. Now, this only involved making sure that the numbers that would make denominators 0 weren't an issue, right? We look back at this problem and we say, well, what would cause issues? Well, if this denominator was 0, well, x can't equal 0, and that's done. Or if this denominator can't equal 0, x minus 5 can equal 0, then move the 5 over, and x can equal 5. So that was a domain check you do at either the beginning or the end of the problem to find those values of x that are not allowed to be answers because they would break the domain issue. Now that said, if x can't be either of those numbers, that's fine. Neither of our solutions were either of the domain issues, so 25 and negative 20 are both solutions. Like we saw in chapter 6, if any of your answers are domain issues, you immediately just get rid of them. They are not valid, and you look at whatever's left. All right, the next one we can see is an equation involving a radical. So this would make it a chapter 7 question. So if you recall, solving a radical equation, we want to get the radical term by itself first. So I will subtract the p on over, giving me 35 minus p. Now the negative 2 can stay there because it is officially part of the one term that involves a radical, but the next step was to raise both sides to the power required, and if it's a square root, then the power is squared. So we will square both sides. So squaring the left-hand side, we saw the negative 2 squared gives me a positive 4, and the square root of p squared gives me the inside. That's why we did that. We wanted to get rid of that square root, get just what was left on the inside. So 4p equals, now remember this is 35 minus p times 35 minus p. Don't just square each piece. Write it out, then distribute. 35 times 35 is going to be 1225. Then we'll have a minus 35p, another minus 35p, and a plus p squared. And then we'll combine these like terms. I'll even bring over this minus 4p here. So I've got p squared. That'll be minus 74p and minus 1225. All right, so the question and the hope would be that this thing would factor. 1225, that's a huge number. If I started saying what are the numbers that multiply to negative 1225 and add 74, you might think to yourself, oh my gosh, I have to try 1 and then 2 and then 3 and then 4. And you could, right? You could go up that route. But let's point out that by the fact that this thing ends in a 5, that tells you that one of your factors has to be a multiple of 5. So let's just start counting up by 5s. But also let's point out that this is a negative 1225, so we have opposite sign numbers, and we need them to add to a negative 74. So they're going to be pretty far apart too, okay, in terms of how far apart they are, so that a positive and a negative would add to negative 74. So again, you can start wherever you want to. I mean, you can even start at 5, but if I take 1225 and divide it by 5, that's 5 and 2, 45, right? Okay, still too far apart. Now, I don't even need to bother with 10, because 10 ends in a 0, and that and any other number would mean this number would end in a 0. So notice how restricting we can be. We're going to count by 5s, but we're also going to skip over every one that ends in a 0. So I'm going to jump right to a 15 and see, does 1225 divide by 15? It does not, okay? How about 1225? I can skip the 20. I'll move on to 25. So it's 25 and 49. Oh, that's where my mistake was made. And that 1225 should be a positive. I apologize for that. That should be a positive 1225, which means we need them to be the same sign, which is now, as I'm looking at these numbers, what I realize. We need a 25 and a 49 to multiply to a positive 1225, but add to a negative 74. So they need to be opposite signs. They need to be both negatives. Negative 25 and negative 49 multiply to a positive 1225 and add to a negative 74. So our easy case number game would be a minus 25 and a minus 49. And that's equal to a 0. So we get p minus 25 equals 0, or p minus 49 equals 0. So 25 and 49 as our possible answers. But then recall that with radicals in chapter 7, because of this squaring both sides step we took, we have to actually check both of these solutions. Check in the sense that we put them all the way back into the problem and see if they work out. So 25 minus 2 times the square root of 25 equaling 35. That's me putting 25 in for both the p's. 25 minus 2 times a 5. So that's 25 minus 10. So that's 15 equals 35. Well, that didn't work. So 25 is not a solution. Throwing in 49. 49 minus 2 times the square root of 49 equaling 35 will be 32, or 49 minus 2 times 7 equals 35. So 49 minus 14 equals 35, which looks like 35 equals 35. So 49 is going to be our solution, our only solution to that equation. And lastly here, what we've got is an equation that doesn't quite look like a quadratic equation, but we've talked about can resemble one. If I bring that x squared term on over, 21x squared plus 80 equals 0, we had the thing called substitution, where we can take this x to the fourth and x squared, and if we pick any other variable like, say, y, and we notice for this specific pattern, if we let y equal x squared, then this x to the fourth is like x squared squared. So if y is x squared, then we would need y squared to represent x to the fourth, meaning we can change this term into y squared. We can change this term into just 21y, right? Replacing x squared with y. And now we have a y squared y, no y. And in fact, it's an easy case where we're just looking for numbers that multiply to positive 80 and add to negative 21. So positive 80 means they're going to be same sign. Negative 21 means we're going to need to be both negative. So what do you think here? What's looking good? 1 and 80, not so much. 2 and 40, no. 4 and 20, no. 5 and 16 is looking pretty good. Negative 5 and negative 16. Multiply to a positive 80, but add to a negative 21. So y minus 5 and y minus 16 equaling 0. So what that means is you get y minus 5 equals 0 and y minus 16 equals 0. So y equals 5 and y equals 16. Now here's a small twist that we actually wouldn't have seen up until now in this chapter. When we bring the x squared back in here, x squared equals 5 and x squared equals 16. Notice we can now solve this. We basically would not have had an equation back in chapter 5. We would have just been doing a factoring process from the beginning. Solving an equation can result with these kind of answers where now I can say square root property, right? If I put that x squared back in place of y, we can use the square root property here to say that x is plus or minus the square root of 5. And here, it even works out nicely, the square root of 16, so plus or minus 4. But notice that is 4 different answers. That's the solutions of square root of 5, negative square root of 5, 4, and negative 4. And as we said a long time ago, it actually makes sense that we see 4 solutions because we talked about how when you have an equation like this with a polynomial, your highest power, your degree of your polynomial, is the maximum number of possible solutions you might see. And so there we are. We have 4 solutions for this equation that was to the 4th power.